When an AI agent gets stuck in a recursive loop or bungles a multi-step data pipeline, the failure is often blamed on the model. We assume it simply lacks the intelligence or the parameter count to complete the job. However, the root cause usually lies in the shape of the workflow and the rigid boundaries of the system's memory. Large language models generate confident, highly structured prose that aligns with human evaluation heuristics. Because we instinctively equate linguistic fluency with logical accuracy, we often assume a plan is sound simply because it is well articulated. This creates a fluency trap, where the quality of the prose masks a lack of underlying grounding. This diagram shows two distinct problem-solving systems. On the left is internal reasoning, a static, isolated process where the AI calculates an answer in a vacuum. On the right is external planning, a dynamic execution sequence where the system sequences operations against a shifting real-world environment. A model can generate a logical internal monologue, but the only valid test of an agentic system is whether its architecture can execute that plan when the actual environment pushes back. To see how this breaks, consider an automated DevOps agent tasked with a complex server migration in a live enterprise environment. Operating on its internal reasoning, the agent outputs an articulate multi-step plan: spend down server A, migrate the database to server B, and update the DNS records. The agent executes the first step of the plan perfectly. The server spends down, and the builder watching the log files sees a system operating exactly as intended. Then the agent reaches the second step. The database on server A is locked by an active background process. The live environment has pushed back. Because the agent was deployed as a static prompting sequence without observational tools, it cannot see this locked state. It has no mechanism to read the specific API error. The agent continues attempting to update DNS records for a migration that never finished, forcing a sequence of actions against a state that no longer exists. The system failed because its static reasoning hit a reality it was never architected to observe. This failure is driven by autoregressive gravity. Language models predict the next token based entirely on the tokens that came before it. This massive block of prior data exerts a mathematical pull on the next prediction, forcing the output's trajectory. Once a model has spent 800 tokens confidently articulating a plan, the statistical weight of those tokens overrides any mean warning signals. The system is mathematically compelled to maintain its trajectory, even if it's hallucinating the path forward. The first architectural fix is task decomposition. Breaking a massive prompt into bounded subgoals prevents the model from being overwhelmed by the weight of its own context. The second fix is the react loop, short for thought, action, and observation. This diagram illustrates how the loop acts as an operational bridge between static thought and dynamic reality. The loop forces the model to test its hypothesis against the environment. It executes a command, receives live feedback from the external world, and adjusts its understanding before predicting the next step. These baseline scaffolds ground the AI in reality, stopping localized friction from cascading into systemic failure. Next is the risk of factual hallucinations within high-stakes workflows, such as parsing complex financial liabilities or sensitive medical records. A common mistake is simply adding a line to the end of a long prompt asking the model to double-check its work. Due to autoregressive gravity, if the model has already hallucinated a legal precedent, it is statistically biased to validate its own error if verification happens in the same window. This is why chain of verification, or COVE, is necessary. It creates a mechanical separation between data generation and factual auditing. The system extracts individual claims, stripping them out without bringing along any surrounding text or its statistical weight. Those isolated claims are then fed to a fresh, stateless instance of the model. This auditor verifies the raw fact without being influenced by the original draft. High-stakes tasks require factual verification to be mechanically separated from generation to prevent the architecture from validating its own errors. For edge cases where a task has many viable paths or potential dead ends, developers look to multi-path architectures like state space search. This diagram shows a system testing multiple branches simultaneously to find the optimal route. It functions like a chess engine, projecting multiple moves ahead to navigate high levels of state space complexity. However, maintaining these parallel traces multiplies API costs and adds significant orchestration complexity. Deploying these complex search layers for standard, deterministic problems is an inefficient use of compute. A mature system architect prioritizes the discipline of restraint. The ultimate objective is to deploy the lightest reasoning scaffold, like simple task decomposition, a basic React loop, and isolated explicit verification that reliably completes the complex task. Once the system successfully reaches that reliability threshold, the design is completely finished.